Greetings, it's Paul with the introductory video for Class 20 of Math 117. This is brand new and we'll have to see how it works out. I spent a lot of time writing a couple of R scripts that illustrate the concepts that I'll be talking about in this video, and I'm hoping this will be the best ever introduction to the Black-Scholes equation. So let's start by thinking about our earlier model of fair pricing, which was based on scratch tickets. I'm totally going to ignore the issue of discounting future values today. That's really a red herring. You can just adjust currency as a function of time so that the problem goes away. And you'll recall that what we did was every day the possible values for the next day were two in number. One was higher, one was lower. And if we had a scratch ticket that was fairly priced at S on day 0, after day 1, its price would either rise to S times U or S times V, and we needed to figure out what the probability of a price rise had to be in order to make the share price a martingale, such that the expected value of the price on day 1, conditioned on day 0, was equal to x0. What's the solution? Well, you say you've got a probability p that the price will go up to s times u, a probability 1 minus p that it will go down to s times d, and therefore the expectation is the sum of those two things. It has to be equal to s. The s neatly cancels out. We get 1 equals pu plus d minus pd. Solve it, and we get a probability of 1 minus d over u minus d. With our early scratch tickets, we figured that out by inspection. Let's consider the simplest imaginable case where p equals 1/2. Now first I want to point out the model we're using has the nice feature that the behavior of the price doesn't depend on the unit of currency. For example, if we say we've got a ticket that's fairly priced at $4 and the next day it will either be up to $5 or down to $3, then U is 5/4 and D is 3/4. And if I restate the situation by saying the ticket is fairly priced at 400 cents, it rises to 500 cents or drops to 300 cents. The change in price is proportional to the current value. If we're going to keep scratching the ticket for n days, it seems reasonable to have the value of p not change from one day to another. When we start dealing with shares, we're going to assume that they have a so-called volatility that is independent of time. Now we set things up so that the fair price is clearly a martingale. The situation is just like betting on red when playing roulette in a fair casino, except that the assumption is the size of your bet is always proportional to the number of chips you have at the moment. In the R script, which I will show you in class, this situation is illustrated by the first of the 5 models that I have coded up. And when you look at what happens after n days, you'll see that the price after n days is very far from normally distributed. There's no way you can go broke, because as you start losing money, you'll make smaller and smaller bets. On the other hand, because you have larger bets to make if you're winning, you have quite a reasonable chance of doubling your original stake. Since this is a martingale, if you start out with k chips, after n spins of the wheel, your expectation is still to have n chips, but the median is going to be less than k. There will be a lot of situations where you are a small-time loser, offset by a few situations where you're a big-time winner. Now, if you write the share price as the exponential of some volatility sigma times a random walk variable w sub t, and think about the exponent, you'll suddenly realize that that wt is not a martingale. Why? because when you lose a greater percentage than what you win when you are successful. To take a concrete example, suppose you either go up by a half or down by a half. If you go up by 1/2 from 1 to 3 halves or from 50 to 75, you have only gone up by a factor of 3 halves. On the other hand, if you go down by 1/2 from 50 to 25 or from 1 to 1/2, you've gone down by a factor of 2. So it's built into this assumption of equal gain and equal loss to get a probability of 50% that your percentage loss is going to exceed your percentage gain, and therefore on the average the exponent will drift down. A nice way of looking at this is to consider what happens if you win and then lose. So suppose you go from 50 up to 75, and then you lose. You go to 1/2 of 75, 37.5, which is less than 50. So if you alternately win and lose, your sequence of wins and losses will gradually take you down. That is, your percentage gain will end up being less than 1. How are we going to fix this? Well, what we want to do is to make the exponent change by an equal amount, whether you win or lose. So to do that, I will introduce a quantity sigma. I will set u equal to e to the sigma, and then I will make d equal to e to the minus sigma. So the exponent will execute a random walk. The probability p is still a half. Half the time it'll go up by sigma, half the time it'll go down by sigma. But now we've got a new problem. If you look at e to the sigma plus e to the minus sigma divided by 2, you realize that's a little bit greater than 1. So your expectation under these circumstances would be for a small increase every day. Now we've made the exponent a martingale, but the share price is no longer a martingale. I've illustrated this situation, as I will show you, by Model 2 in my R script. And we already know the fix, because we proved that sigma times wt minus sigma squared over 2 is a martingale. So what we do is introduce a quantity mu equal to minus sigma squared over 2, and we multiply the share price by e to the mu times t each day. This resulting downward drift is just sufficient to keep the expected share price constant, and you'll see that very nicely when I run Model 3 in my R script. Now when we do a simulation of lots and lots of random walks, we can extract the exponent by saying the initial price, x0, gets multiplied by some exponential to get the final value, x sub n. If I take the fraction, x sub n over x0, by which the price increases, its logarithm is the resulting exponent. It will turn out that because of the drift, this quantity will have a negative expectation. But if you remove the drift from it, what's left in the exponent is still a symmetric random walk. This is symbolized in Deneen by w sub t with the tilde over it, and it turns out that for lots of small steps, this is normally distributed. It has an expectation of 0 thanks to the drift, and it has a variance proportional to the number of steps, because it, like w sub t squared minus t, is also a martingale. So now we've introduced drift, and you might ask, well, can I do things with any drift I like? The answer is yes. So what I'm going to do is introduce two quantities now, a volatility, sigma, whose exponential e to the sigma I will call v. That's the amount by which you multiply if you get an up step, and by which you divide if you get a down step. But I'm also going to introduce a drift mu, whose exponential I will call m, and whether we go up or down, we'll always multiply by m. In other words, if the price starts out at s, either we will go up and I will multiply it by m and by v, or it will go down, I will divide it by v, but I will still multiply by m. For the share price to be a martingale, we still need p times the higher price su plus 1 minus p times the lower price sd to be equal to s. I can factor s out of that equation and substitute in the appropriate values. U equals mv and d equals m times the inverse of v. Set that equal to 1, solve, and I get a formula for the probability in terms of m and v. Once I've chosen m and v, I know what risk-neutral probability I need in order to make the share price a martingale. In the exponent, we can still think of a random variable, let's call it a sub I, that has probability p of equaling 1, probability 1 minus p of equaling minus 1. This is an unsymmetric random walk if p is different from 1/2. And it's the sum of these variables that is responsible for the exponent. It gives us the random part of the price evolution, while the drift gives us a non-random part. And it turns out that in general, this w sub n is not a martingale. It will only be a martingale if p equals 1/2. But it's always possible, and you get plenty of practice in doing this, of finding some constant, call it capital C, to create a slightly altered random variable, w tilde t, which is equal to wt minus your constant times t, and that you can make a martingale. This will be illustrated nicely by model 4 when I run the R script. Finally, you might ask, can I actually create a process with arbitrary p, and does it make any difference? This is the subject of the 5th and final model in the R script. We can pick a volatility, and we know that the risk-neutral probability has to satisfy the usual equation that the probability of going up times the factor by which you go up, mv, plus the probability of going down, 1 minus p, times the factor by which you multiply if you go down, mv inverse, has to equal 1. I can easily solve that for m, and I have a formula for the drift that I need to introduce in order to achieve any desired p. Suppose, for example, I want to make p significantly larger than 1/2. In that case, I will have a fairly big p times a number that's greater than 1 plus a smaller 1 minus p multiplied by v inverse, which falls short of 1 by a little bit less than v exceeds it. Under those circumstances, m will turn out to be slightly less than 1. And what's going to happen is, with a probability close to 1, we'll get a lot of up steps and very few downward steps, but because m is less than 1, the drift will be dragging things down, so the upward steps will be small, the downward steps will be large, and we will still have a martingale both in the exponent and for the share prices. When you look at graphs of the time evolution of the price, this looks highly significant. However, you'll discover that for a large number of steps, the distribution of prices after n steps won't be much different from when it is in the simpler case where p equals 1/2, and the reason is the central limit theorem. As long as we have a random variable with zero expectation, the sum of many independent copies of that random variable will approach a random variable with a normal distribution that depends only on the variance. And while the variance is a little bit different when p is different from 1/2 to what it is with a half, that doesn't really make a big difference. So it's v rather than m that's going to turn out to be the important thing. Now let's think about what we can do with the binomial distribution. What's an element of our sample space? Well, it's just a sequence of n ups and downs. We get an up with probability p, we get a down with probability 1 minus p, and as everyone learns in high school, the probability that we'll get a sequence where I out of the n symbols will be ups is n choose I, to take into account the number of places you can position the p's, times p to the I, the probability for having something with probability p happen I times 1 minus p to the n minus I. And what's that sequence going to do? It's going to take a price that starts at x naught and cause it to evolve to x naught multiplied by u to the I for the I upward steps, and multiplied by d to the n minus I for the d downward steps. After n steps, because x sub t is a martingale, the expected price is still going to be x0. However, using just the binomial distribution, we can answer a lot of questions without looking at the details of the intermediate steps. In particular, we can calculate the probability of any specific final price. We just ask, how many up steps does it take to reach that price, and what is the probability of getting that number of up steps out of n total steps, given the probability p of an up step. If we're thinking about an option with a strike price p, we can answer the question, what's the probability that the final price will exceed some specified strike price? We just ask, how many up steps do we need in order for the option to be in the money? And then we ask, what's the probability that with a binomial distribution, we will get at least that number of up steps? Unfortunately, there's no simple closed form expression for that result. It's conveniently built into the R scripting language, so I'll be able to do it easily on a computer, but it's a tedious thing to do with pencil and paper. Finally, suppose we want to know the expected value of an option. Well, if we can calculate the probability of any final price, then it will be perfectly easy to calculate the expectation of the amount we receive from the option if it's in the money. So in principle, from the binomial distribution, we can figure out the fair value for call options. And the only snag here is that there's no simple closed form expression for the distribution function of a binomially distributed random variable. So what we're going to do is take advantage of the central limit theorem. The central limit theorem says that the limit of a binomial distribution, in the case where we have a very large number of trials, is a normal distribution for which there is a well-known formula for the probability distribution function, though it's not expressed in terms of elementary functions. And when we start working with the normal distribution, we're going to end up with the Black-Scholes formula. But the only thing new is going to be that we're trading in our binomial distribution for a normal distribution. Other than that, if you understand what's going on today, you will understand Black-Scholes. And with that comment, I am done.